17. Okay. Number 17. I asked you guys to figure out equation. Now, the idea was you're supposed to use the line regression in your calculator. Either line regression, quad regression, power regression, exponential regression. Now, the reason why is because if you think of physics as like a superhero, okay, we'll go with Batman. So physics is like Batman, okay? Now, what is math to physics? Anybody know? It's our tools, right? Batman's utilities belt. So math and physics go together like Batman and his utility belt go together. Now, I'm assuming that we understand how to solve algebraic equations and how to use regressions and anything else that you did in 10th grade math. Okay? So sine, cosine, tangent, all that stuff is assumed that we understand how to do. All right? So if you don't, then when we come to those, make sure you get extra help from me. All right? So line regressions is one thing you do in 10th grade math. So for number 17, I asked you to find a regression equation for our graph, right? Now our graph looked like this, didn't it?
Yep.
Caleb, you said it was half of a what? Parabola. Now what's this axis again?
Y.
Okay, it's the y. It's also the position, right? Okay. It's our position axis, right? What's this one?
X.
X. It's also our time. Okay, Amanda, you got a question? Okay. Well, let's focus on this, please. Now, you guys are supposed to find multiple regression equations. Now, what is the best R value you can get for a regression equation? 1. Did anybody get an equation with an R value of 1? Okay. Nan, what was it? Yep.
Y equals AX squared.
Okay, so we'll plug in the A's.
I don't have it.
You don't have it?
I have it.
Okay, Skylar?
Y equals 2.5x squared plus 2.5x plus 0.
Well, that's what I got.
Oh, 0, not C.
But now don't we have to make it into our thing?
Yep. So now we're going to take this equation, and the reason why I had to do this is because you guys are creating the next equation to go on the board. Okay. How do we come to that? We plugged our data in from number 11. Yeah, from 11 into list 1 and list 2 in our calculator. Okay. And then we did you know how to do that? You know how to plug it in? Stat, edit. Okay. Then hit stat, go to calc, and there's a list of different regressions. You have linear regression, quadratic regression, cubic regression, quartile regression, or not quartile.
It's a quadratic.
No, not quadratic. That's 2. Quartic. There we go. Quartic regression, and then there's also power, exponential, and logarithmic. And you try all the regressions, whichever one has the highest R value, the R value closest to 1, that's your best regression equation. And this one had a regression equal to 1, which means it's right on.
This one says it's
Okay.
I got a quadratic.
This is a quadratic.
You said it was. No, I said it's quadratic.
Okay.
Quartic.
No, this one right here is quadratic, but there's another option there called QUART, which is quartic. It's 4. Yes.
I think I know the thing.
You think you know the things? Okay. So what ones do we know, Katrina? Because the last part of 17 was take this y equals equation and put the d's, the t's, the v's, and the a's in here, right? Right, guys? So in here, what is the position variable? Well, Katrina says she thinks no. What is it, Katrina?
Never mind.
No, let me know. I want to write down.
Okay, I thought it was 2.5b squared plus 2.5a plus v0.
Okay, so 2.5 v squared plus 2.5 a plus v0.
Will be not.
Okay, and what goes over here? What's it equal to? Now, in general, we're using a y equals equation, right? Now, why did I want to make a point of knowing what d's or what y was and what x was?
Because
you like to make points.
I do like to make points, so that's part of my job.
So you know the distance.
We know that y is what? D, and we know that x is
T.
because that's the graph we used, right? Okay. I appreciate the effort, though, Katrina.
It's
Hold on a sec, Scott. So y we said was position, right? Now is this initial or final position?
that's
Final. It's the position at a specific instant in time, right? Okay. So that's our final position. Okay. Juan, can you see us back here? Or should I move over there? We'll move over here.
he's good.
So y equals 2.5x squared plus 2.5x plus 0, right? And we said that our y was
Position.
position, right? Because that's what it is over here, right? And if I go to this spot right here, that's that position at this specific time. Okay, right? That's the position at this specific time. So that's why I know it's D final. Does that make sense?
Yeah.
Okay. What's the x going to be?
Time.
Time. Okay. So everywhere I see an x, we get t. Now I deliberately left openings there, and not because I want to fill in the 2.5, okay, but I want to fill in what the letters are, right? What the coefficients are. Now we were supposed to use, the coefficients we were supposed to use were position, right? Velocity, time,
And acceleration.
and acceleration. Now this position breaks into two. It can break into D final or D initial, right? Okay. This velocity, same thing, could be V naught or V final. Okay. So, what else do we think we know? Sky, you got another one?
Acceleration is the t squared because it's, you know, the answer for acceleration is always squared. So, you know, like meters per second squared.
Okay. So the unit for acceleration is meters per second squared, right? So Skylar's exactly on the right track here. The unit for acceleration is meters per second squared, right, guys? Right? I want this to equal a, what's the unit here? What's the unit? It's position, what's the unit? Meters, right? So how can I take a meters per second squared
Cancel the time.
and turn it into a meters? What do I got to multiply by?
That's
Second squared, right? Is there anything here that gives me second squared?
t squared.
The t squared. So what goes there?
Acceleration.
Acceleration.
And then
Okay.
velocity goes with t
Why?
because it's just meters per second.
Okay, so because this equation ends in a distance, right? And velocity is meters per second, what do I have to multiply velocity by to turn it into meters?
Second.
You gotta multiply by seconds, right?
Yeah.
So that means my velocity goes where?
Right there next to t.
To t. Now, is this an initial velocity, an instantaneous velocity, or a final
Instantaneous.
velocity?
Instantaneous.
Okay. If it's instantaneous, will it change over time?
No.
If it's instantaneous, will it change over time?
Yeah.
Yeah, because we're accelerating, aren't we? Right? We're looking for a constant here, right? Not another variable.
So final.
Nope, not final.
Initial.
Initial. So this has to be our initial velocity. Okay. Does that make sense? So we're almost done. There's two more things to add. Okay. Now, where did the black car start in the problem? Where does the car start on this graph?
0.
0, right? This spot right here where we cross this axis, that's called our y-intercept. It's also our
D naught.
D naught. Our initial position is where we cross that axis, right? So in this problem, we crossed at 0, didn't we? So that means that this 0, which is overlooked by some of you, is a very important piece. What piece is that?
D naught. Start at.
It's our start at. It's our D naught. Right? Does that make sense?
I'm not gonna lie, I'm so confused.
We're taking, well, did you do number 17?
No, I don't know.
That's probably why we're confused. Okay. I know, but then that's also classroom usage yesterday, right? We had enough time to go through it yesterday. I could have helped you with 17. That'd be,
I know, but I got done. Right, I got to 17 right there.
I can still help you with it, right? All right, so what's next? I said there's two things, right?
Mhm.
We only added one. There's one more thing we have to add.
Vectors.
Okay, it's a good thing to add though. We should add vectors. We already have D final. There's one more thing we need to add. Now, what do you know about the black car's acceleration?
It accelerates by 5 meters a second.
We know for this specific problem that acceleration is 5 meters per second squared. That means each second this slope is increasing by 5 meters per second squared, right? Right? Where's the 5 in the equation? Because if this is supposed to match, if our y equals equation is supposed to match our equation that we're making right here, our general equation, then where's the 5?
The 2.5. Because it's.
Well,
meters
that's-
squared.
That's not a 5 though.
Well, you gotta square root it because the 5 isn't squared, the seconds are.
Square root 5, what do you get? You don't get 2.5.
Not squared. Oh, wait.
So it's not square root,
It's.
okay? But the 5 should be here by the t squared, shouldn't it?
Yeah.
So what happened to it?
Disappeared?
Didn't disappear.
It.
What is it? 2.5 plus 2.5 is what? 5. So I think I heard Skyler say it. What happened to that acceleration?
I have
It halved, right? So what do I need to add to this equation? Not times 2. What do I need to add right here?
2. Oh, half.
1/2. 1/2 AT squared. Right?
Let's make one like this.
No, I expected you to get this on your own, Katrina, which most of us got, right? And then, I mean, if I pressed you to and then had you guys work in groups for like 2 hours, I bet you could probably figure that out, right? Or we could just, let me add 2 hours.
Probably not.
That's just an arbitrary time. Maybe a half an hour longer. If we had 90 minutes yesterday, you probably could figure that out. Okay. But I think you could have.
With a lot of you.
Yeah, with a lot of help.
All right. All right. So does that equation make sense?
No.
Oh, yes, it does.
Yeah.
Now, if we look, is this a quadratic equation?
Yeah.
Yeah. If I graph this and I plug in numbers for A, V naught, and D, will it make a parabola? Yeah. So this is the equation for that line right there. Okay. And like you said, it's a parabola. So on a position versus time graph, it's going to be curved. This object is accelerating. It's going to be curved, right? Now, what if my acceleration is 0? What happens to this equation? What if acceleration is 0?
You take out the t squared.
Then the t squared goes away, doesn't it?
Yep.
So we have 1/2 times 0 t squared plus v naught t plus d naught, right?
Mhm.
What happens to this?
It goes away.
Comes 0. And then does this look like an equation we've seen before?
Yep.
Yeah. So if I have no acceleration, I have this equation which gives me a
Constant velocity.
constant velocity straight line, right? If I have acceleration, I have this equation which gives me a
Acceleration. Like increase in velocity.
a curved line.
Increase in
right?
velocity.
Okay, this is a parabola, right? This is a line.
What's my mind?
No, you can always get your equations. Now you should know though that if I have an acceleration, my graph's a parabola because my acceleration changes my velocity, changes my slope, right? If I don't have an acceleration, then I get a line because I have no acceleration. My velocity is constant. All right, does that make sense?
Yes.
All right, are there any questions?